Hey everyone, this is Danny, and this is my presentation on alignment algorithms for biological sequences. As many may already know, biological sequences include DNA and protein structures and are often represented by strings of letters. For DNA, that includes GACT, and down here you can see letters representing various amino acids. Finding similarity in sequences can provide information on functional and evolutionary relationships. This problem is the basis of sequence alignment programs such as BLAST and CLUSTAL. My project focuses on pairwise alignment techniques, or the alignment of two sequences. Here is a simple example of two sequences being aligned two different ways, each providing different alignment scores. These scores are affected by matches, mismatches, and gap penalties. And multiple optimal alignments are often possible. For this project, I decided to look at three algorithms. The first algorithm I analyzed was the Needleman-Wunsch algorithm, which is a global alignment algorithm that is best used for sequences of similar length. The two other algorithms I chose are variations of the Needleman-Wunsch. There's the Smith-Waterman algorithm, which is very similar to the Needleman-Wunsch, but it's tuned for local alignments, which focus on areas of high similarity. The last algorithm is Hertzsprung's algorithm, which is a divide and conquer modification of Needleman-Wunsch that takes a linear space, instead of quadratic space, and it can also be applied to Smith-Waterman. The first algorithm I will be analyzing is the Needleman-Wunsch, which is a global alignment algorithm. So global alignments are used to align sequences of similar length and attempt to align the entirety of both sequences. The general algorithm starts with initializing a scoring matrix and its corresponding traceback matrix. You then would calculate and fill out the scoring matrix using a similarity matrix and fill in the corresponding traceback matrix. Finally, you retrieve the optimal alignment from the traceback matrix. Here's an example of a similarity matrix, which contains the match scores between all amino acids. This is used to fill in the scoring matrix when you start to align the sequences. And this particular matrix is called Blosum 50, and it's actually it's a pretty commonly used matrix. So on the left, this is the scoring matrix on the left, and this is the most important matrix. And each cell represents the optimal score for the alignment up to that cell, and each score is calculated as the maximum from three cells: the cell before, the cell above, and the cell diagonal above, I guess. When filling in the scoring matrix, we also fill in the traceback matrix at the same time. The traceback matrix contains pointers to where the score for each cell in the scoring matrix is calculated from. And the final optimal alignment is achieved when you trace back the traceback matrix. And this is just an example of tracing back the traceback matrix to obtain the optimal alignment. So when you trace back diagonally, you just fill in when you trace back diagonally, you are aligning the sequences. So tracing back diagonally 2 times from the bottom right box, you align D and N. And when the traceback traces back to a cell before it or above, you place a gap. So in this case, the arrow is pointing towards the A, so you place a gap. So a gap is aligned with E, and then there's another diagonal, the final diagonal pointer. In that case, you just align S and A. So this is the main segment of code for the NW algorithm, and the main variables to look at when analyzing the algorithm are the length of the two sequences. Over here we have n equal to the length of sequence 1 and the length of m equal to sequence 2. For the first part of the algorithm, we see 2 loops. These loops fill in the single gap row and gap column during the score matrix initialization. You can see it here, the -10, -20, -30, -40. Those are always placed when working with the Needleman-Wunsch algorithm. Filling in the single row and column takes ON and OM time. The main part of the algorithm is the score and traceback matrix traversal, which takes big O of n times m time. And although each cell requires a number of calculations to find a maximum score, the number of calculations are constant. The final part of the algorithm, which is actually not shown here, is the actual tracing back of the traceback matrix, and that takes at most n or m time, depending on which is the maximum, and it will never go over that. And assuming that n is a longer sequence, the final time complexity of the NW algorithm is O of n plus O of m plus O of n times m plus O of n, and altogether that's just O of n times m time. The space complexity is relatively simple to calculate for the NW algorithm. Because it focuses on two matrices of size n plus 1 times n plus 1, the space complexity is just O of 2 times n plus 1 times n plus 1, which just turns out to be O of n times m time. The next algorithm is the Smith-Waterman algorithm, and it's very similar to the NW algorithm. The main difference is that the SW algorithm performs local alignments, and local alignments finds regions of high similarity between two sequences and does not attempt to align the whole sequence, unlike the NW algorithm. The SW algorithm is thus useful for sequences of varying sizes. There are two major modifications within the SW algorithm that differs it from the NW algorithm. The first is that the matrix scores are not allowed to go below 0. This allows the algorithm to restart at any pair of aligned residues, and so it's able to compare subsequences of all possible lengths. The second difference is that traceback starts at the cell with the highest score instead of the cell that is calculated last. I don't think I mentioned it earlier, but yeah, the NW traceback requires tracing to start at the last cell since we are aligning entire sequences. For the SW algorithm, since we are looking for optimal local alignments, we don't need to start at the end. For the most part, the actual algorithm of SW is similar to that of NW. One difference is that, at least in this implementation, we do not need to worry about filling in the gap rows and gap columns because we know that the gap cost would just be 0, since we cannot go below a score of 0. It is common for the gap row and column to be implemented, though. It's just not in this implementation. And another difference is that when we score each cell, we have to make an additional comparison to 0, since again we cannot go below a score of 0. Tracing back is also O of n time, but we do not necessarily have to start at the last cell, so tracing back may be faster when both algorithms are comparing the same sequences. The final time complexity of the SW algorithm is then just O of n times m plus O of n, which is just O of n times m. Space complexity is also similar to that of NW, as they utilize the same scoring and traceback matrix. One minor difference that may or may not affect space performance is that in this implementation, traceback cells contain a null value when the corresponding scoring matrix cell has a score of 0. The last algorithm to analyze is Hirschberg's algorithm, which is a pretty novel implementation, or well, it was a novel back in the days, is of the NW algorithm. It utilizes a divide and conquer strategy and can be implemented for global and local alignments, and it produces the same optimal alignments. There are two ideas behind this algorithm that Dan Hirschberg cleverly suggested. The first is that only two rows need to be stored while working on the matrix, the current and the previous row. This is because when you're filling in the score of a cell, you only need to take the max from either the previous cell, the cell above it, or the cell diagonally before it. And these cells either lie on the current row or on the previous row. The second idea is that an optimal alignment can be retrieved by recursively dividing up the sequences into subsequences and working on each resulting matrix separately. And by utilizing these ideas, a linear space algorithm is possible with the same time complexity as NW. Here's an example of a matrix that has already been divided into and traversed. The top matrix is traversed normally, but the bottom matrix is always traversed from the bottom to top in the opposite direction of the top matrix. This creates a sort of convergence at the center, and that's where the optimal cells for each matrix meet. This convergence contains the cells from where the final alignment passes through. By recursing through these matrices, we end up with the final path without actually needing a direct trace path. And here's the rest of the steps for the previous matrix. Aside from the initial two halves, the recursions after also split the matrix vertically at the point where the optimal convergence was previously found. So this results in 2/4 of the matrix being worked on in every recursion. It's also important to note that only 2 rows are being worked on and stored at any one time, and so rows are swapped continuously to traverse the whole matrix. So this is the algorithm to solve each subproblem of each recursive step. The recursive part of the algorithm is shown in a bit. Like the NW algorithm, it still needs to initialize the gap row, but because we are traversing the columns one by one with a 2-row array, we cannot fill out the gap column beforehand. So it takes O(n) time to fill in the initial gap values instead of O(n) plus m, like the NW algorithm. And to fill out the initial 2 halves of the matrix, O(n) times m is still required since the whole matrix is still traversed. As mentioned before, the algorithm does not require a direct traceback. Instead, the optimal convergence cells are stored in another matrix. So this is the recursive portion of the Hertzsprung algorithm, and it splits the current scoring matrix into smaller subproblems. The initial alignment takes O(n) times m time, as 2 halves makes a whole. But for every iteration of the algorithm after, we work with 2/4 size matrices of the remaining matrix and so forth. So the total time complexity of the recursion is it's O of n times m times 1 plus the recursion halves, or recursion quarters, plus half plus a quarter plus 1/8, which just ends up being big O of 2 times n times m. So the total time is just O of n times m. And consequently, this is also the total time complexity of the entire algorithm. The space complexity of Hertzsprung algorithm is where it shines over the previous 2 algorithms. Because only 2 rows are being worked on at once, we only need O of 2 times n space, which is just n. We also need to hold the optimal cells, but this does not exceed n plus m size. And assuming that n is greater than m, this leaves us with O of 2 times n, which is again just O of n. So the total time complexity is just O of n. This is linear space, as opposed to the quadratic space required by the previous 2 algorithms. Okay, so we finally get to the testing portion of my project. And to test the 3 algorithms, I generated random protein sequences of length 100, 300, 500, and so on, incrementing by 200 up to 2500 residues. Each algorithm was ran 50 times for each sequence length, and the timings and memory utilization was recorded. In particular, I'm interested in finding how the Hertzsprung algorithm compares to the other 2 algorithms when concerning space usage, since that is the major draw of the algorithm. And here are some of the specifics on which I performed the test with. It's nothing too fancy. I had to use JProfiler to measure memory use because the built-in NetBeans profiler was kind of buggy for me. So here are the timing results for the 3 algorithms. And from the graph, we can immediately see some anomalies. But before we get to that, we'll look at the first half of the runs, which for the most part is what we expect in terms of relative timing. NW and SW are pretty close to each other in the first half, with the Waterman being a little bit slower. I'm not sure if it's the extra calculations required to compare the max value to 0 in the Smith-Waterman. I'm not sure if that contributes to the slower time. And as we mentioned before, Hertzsprung runs in O of nm times, but more specifically, it runs in O of 2 nm, which is what we see in its first half, as it's roughly twice that of NW and SW, which are both O of nm. So that part looks pretty good. Of course, things get pretty messed up once we reach the later lengths. As you can see at 2100 residues, the NW takes a really large jump in time, up to a second for a run, whereas SW stays pretty low. And actually, Hirschberg begins to catch up in speed, and the algorithm actually overtakes NW and SW in terms of speed later, which is not what we expect since Hirschberg in design is supposed to run slower. It's surprising, but we maybe will explain that later. And moving on to the testing results for memory usage, the results did seem a bit more stable in this area, aside from the strange anomaly at that one dip for the SW. I'm not sure exactly what happened there, but the dip was consistent for all 50 runs. And perhaps the best thing to take away from these results is that the Hirschberg algorithm dominated in space efficiency. It utilized the least amount of memory and it stayed consistently low in usage. And another interesting thing to note is that for the Hirschberg results, are the matching memory usages for different sequence alignments. Like, for example, from the 1300 residues to the 1700 residues runs, they all utilize the same amount of memory. I don't have an answer to that yet, but it's quite curious. And I've already went through most of this. So I was curious about the Hirschberg running faster than NW and SW, so I started looking up on reasons why. And a paper by Driga and his lackeys, they found that Hirschberg actually outperforms NW and SW in practice due to memory caching effects. I'm not sure if this is what I observed in my timing runs, but it's one possible explanation. Another potential problem was the traceback class for the NW and SW algorithms. For some reason, the class consumed the majority of memory usage, over 75% utilization in most cases. This may be due to poor implementation, or maybe it's normal, but it could be the culprit behind the wild jump timings. And actually, one last thing to note is that I actually ran the three algorithms aligning sequences of 9,000 residues, and the results were, again, heavily in favor of Hirschberg's. And the NW and SW algorithms took over 20 seconds to run, whereas Hirschberg took only 2 seconds. And additionally, the NW and SW algorithm required a lot of memory. In this case, the NW required 2.55 gigabytes, and SW required 1.87 gigabytes, whereas Hirschberg only required 43 megabytes, and that's only twice the memory used at 2,500 residues. So Hirschberg algorithm is pretty awesome. So anyways, that's it for my presentation. Thanks for watching, and bye.